Session is being recorded. Thank you. And then, as always, just go ahead and type in your questions. So what we're going to talk about today is something called maximum power transfer. And it's going to make a lot of sense to you because of everything we've covered so far. So again, we know that power generated is determined by the equation P is equal to I squared times R. Great. Thank you, Richard, for joining. And if you look at the circuit to the right, and again, let me grab my writing utensils. I'll pick red here. We look at this circuit. Now, we know that this circuit is a representation of a much larger circuit. I know you can't see it until I'm finished drawing, so you should be able to see that, right? But we can actually simplify a very large circuit into this basic two-element circuit, some Thevenin voltage and some Thevenin resistance. And then whenever you plug in a load, and in this case, we're going to talk about a varying load, we want to make sure that we get the maximum amount of power transferred to that load. And so this is how we determine the power peak transfer and the types of loads that a particular circuit can actually support. Now, I want to actually show you something real quick before we go to the next slide. Forget the math that you're seeing here. For example, on the left side, there are some derivatives written there, and that's for a much more advanced mathematics class. But if you look at the circuit here, we have a source voltage, we have one resistor, which is a Thevenin resistance. Now, again, this is just a model of a more complete circuit. But when you put in a circuit across points A and B, we end up having something that looks like, and let me draw this with another color. Supposed to be there you go. We have two resistors across a source. And we've done this basic circuit before, like in week 2, and it was called a voltage divider circuit. So we know that the proportion of voltage being distributed between the second resistor is a ratio of both resistances, right? And if you think about it that way, it kind of makes a lot more sense on what we're going to talk about next. I don't want to spoil it, but it ends up that when you want to, I'm going to spoil it. When you want to get maximum power transfer, your load resistance has to match your Thevenin resistance. When they're equal, you have an equal distribution of voltage across both, and you have the maximum power transfer. Right? And we'll see that in the next couple of slides. So again, let's use an example of having 10 ohms as a Thevenin resistance and 10 ohms as a load resistance. So it says in this circuit below, the load resistor is matched to the Thevenin resistance. How much voltage drops across the load resistor? So if we have 20 volts for the source, and I can tell you right now, it doesn't really matter what those resistors are, because I have two and they're equal to each other, I know that the voltage drops across both resistances have to be equal. So they're both divvying up that 20 volts equally. If they were both 5 ohms, if they were both 10 ohms, if they were both 20 ohms, it doesn't really matter what it is, but they're both actually taking half of the voltage because they're both just as strong and they both want part of that voltage drop. So the voltage drop is going to be half of the 20 volts per resistance, 10 volts. So without doing any calculations, and if that doesn't make sense, go ahead and try it with different resistances and go ahead and use Ohm's law, go ahead and use Kirchhoff's voltage law to actually define the voltage drop across the load resistor, and you'll see that it doesn't really matter what the value of each of those resistors are. As long as they're equal, you're going to have 10 volts being dropped across both. And again, if you made them unequal, you know that that proportion, that ratio, is going to actually determine which one gets a bigger voltage drop versus the other resistor. And so again, this whole lecture is going to be more about concepts, but just thinking about that concept, we know that if you want a large voltage drop across VL, that it actually has to have a larger resistance. If you wanted to match the voltage across the 10 ohm resistor and you want these things to be equal and matched, then they have to be the same, if that makes sense. Let's look at another question here. So in the circuit below, the load resistor is matched to the Thevenin resistance. How much power is absorbed by the load resistance? So what do we have here? 20 volts. And we know that we're having a, what was the voltage drop across the 10 ohm resistor? 10 volts and 10 ohms. And so for this one, if we want to look at voltage being absorbed, let me go ahead and type this out. We're not looking at voltage being generated, which is VI times R. We are looking at power is equal to I squared times R. Oh, you guys can't see that. See if I can give it to you in a different color. Okay, let's try that again with a different color. Power is equal to I squared times R. So if we look at the current going through both of these resistance, so again, doing an equivalent resistance would be 20 ohms because we're adding two resistors in series. And we're looking at the current. If we use Ohm's law, V equals I times R, we can solve for current. And so current would be equal to, anyone? Yeah, I know you, I can't hear you. I'm trying to do this in my head, actually. Ohm's law, V equals I times R. R is equal to V divided by R, so 20 volts divided by 20 ohms. And so current would be 1 amp. So we know that we'd have 1 amp going through this circuit. See if I can. And so since I have 1 amp going through the circuit, 1 amp times 10 ohms. You see, I'm just going to write it out like this. It's not going to look very pretty. 1 amp times 10 ohms is equal to 10 watts. Right. Okay, great. Now let's look at this same circuit, and we're going to ask something slightly different. In the circuit below, and this is just a twist that the author likes to give you, in the circuit below, the load resistor is matched to the Thevenin resistance. So just like before, how much power is delivered by the voltage source? So now it's just asking how much power, where is it, is this being delivered? Again, this kind of goes back to that same concept we did 2 slides ago, where it doesn't really matter what those resistances are. As long as they're equal, we're going to get maximum power transfer. We're going to get what's called impedance matching. So we're going to get the maximum power out. But in this case, he's just being a little tricky, and he's saying how much power is being delivered by the voltage source. In this case, we're looking at V. So in this case, we know that another equation for power is equal to I times V. We already know that we have 1 amp and we have 20 volts. And so we have 20 watts being generated. So the maximum, if we divide the power up properly, we'd get 10 watts being absorbed by the 10 ohm resistance. And again, that 10 ohm resistance is a model of a much more complex circuit. So if you add up all the individual powers of the complex circuit that we simplified to get this Thevenin circuit, all those little power drops should equal 10 watts. And then we'd have 10 watts being dropped across the varying load. But then again, I just want you to make sure that you understand, if you look at this just like a voltage divider circuit, for analysis purposes only, that's basically what we're looking at. We're looking at a Thevenin circuit with a varying load, and now we can just break this down into a voltage divider circuit. Now, if I was doing a Norton equivalent, remember that's a current with a resistance in parallel, that's actually going to make sense from a different perspective of why these two impedances need to match. And I'll show you that. If it's not in this slide, I'll show you that example. All right. So suppose that we vary the Thevenin resistor instead of the load resistor. For what value of the Thevenin resistance is maximum power delivered to the load resistance? So I have to reread that again. For what value of the Thevenin resistance is maximum power delivered to the load resistance? So it's saying here that when Thevenin resistance is 0, you're going to get all the voltage and the power transferred to the load resistor. Kind of makes sense, right? So if there's nothing else taking up any of the voltage, any of the current, and it's all being absorbed by the 10 ohm, by the load. Again, this is just for analysis. We wouldn't actually do this. This is just for a concept, understanding of a concept, that the maximum power would be transferred to the load resistor, the 10 ohm resistor, if we were to actually make the Thevenin resistance 0. So I want to go back real quick and then kind of discuss this in a different perspective. So imagine that we had a Norton equivalent, and we know that a Norton equivalent and a Thevenin equivalent are the same thing, except for they look a little different. This kind of helps understand the circuit a little better when we're talking about maximum power transfer. All right. And some of you already know this, even though it may have not been explicitly said in the textbook. If I have some resistance, some load resistance, what is the maximum resistance, the highest resistance I will be able to get out of this, that I can actually set this load resistor to get the maximum voltage drop? All right. And we'll just say voltage drop A to B. And we'll call this the Thevenin resistance. And it kind of makes a little more sense when you think about the Norton equivalent. So remember that we talked about resistances in parallel. So the equivalent resistance of resistors in parallel will never be larger than the smallest value. So for example, if I had 100 ohms for R Thevenin and I had 5 ohms for RL, and I do the equivalent resistance is always going to be lower than that 5 ohm resistance. And we know that if we have a very small resistance here, RL, we're actually going to have, using V over R squared, we're actually going to have a very low power loss. I mean, very low power absorbed across RL. So what we want is this voltage across RL to be the maximum. That means that we need to have that equivalent resistance to be maximum between A and B. And the only way we'll do that is that RL has to equal R Thevenin. So now let's look at that same example. Let's say we had 100 ohms for R Thevenin and we had 100 ohms for the load resistance, and we do the equivalent resistance. And we can do this off the top of our head, because if they're both equivalent, the maximum that we'll be able to get is which will be half of both. In other words, 100 ohms divided by 2, which gives us 50 ohms. So the equivalent resistance across A and B will be 50 ohms if I had 100 and 100 on each side. And that's the max you'll be able to get. And you can go ahead and try this by plugging in a bunch of different numbers. Pick any 2 resistors and start working below where one doesn't match, and matching it and then going higher. And you'll see that it never actually gets past that minimum resistance. So in other words, your 2 resistors, you're going to have a point where it's only going to reach some peak and it'll go right back down. And that peak right there is going to be the point where R Thevenin is equal to RL. So go ahead and try this on your own, plug in a bunch of different numbers, use the table if you want, and you'll see that it'll never reach that. That's going to be, because that's the highest resistance we can get, equivalent resistance with this Norton circuit or even a Thevenin circuit, that is the maximum voltage drop we're going to get across A and B, and that's going to be the maximum power being distributed across the load, whatever the load may be. And why do we want maximum power transfer? Well, we want maximum power transfer because we don't want to lose power. We don't want to be creating a circuit where we are dissipating power as heat, and we're losing money basically, because power is money. And that's really all I wanted to cover for maximum power transfer. I'm not going to actually make you do any of the rest of this. So basically, what's going on for the rest of this slide is we're actually going to ask you to reduce these circuits down to Thevenin equivalents so you can determine maximum power transfer. But you know how to do all this. You know how to do mesh. So I'm not going to go over that. I just really want to go over the concept. Right? And again, a technique for circuit analysis, Ohm's law, KVL, KCL, combining resistors in series and parallel. Again, doing voltage division and current division, and then picking one of the analysis techniques, either node voltage, mesh current, source transformation, or Thevenin and Norton equivalents. Right. Okay, so that ends for the lecture for maximum power transfer. I'm really more concerned with the concept. And what I want you to do now, what I'm going to do for you now, is actually tell you what's going to be on the exam, which is on Monday the 30th. Now, I know one of you has to take the exam early because you've got military obligations. That's perfectly fine. I will set up a time so that you can actually take the exam this week. Now, let me give you a blank sheet so we can actually, let's see what we got here. Share the blank whiteboard. Okay. So, study guide for the exam. Hopefully my microphone reaches. For, we'll call this midterm. One, the exam will have 4 questions, 4 problems. Problems? And I'll do it like this. It will have 1 circuit for mesh analysis, 1 for node voltage, 1 where you're going to do a Thevenin equivalent, and 1 where you do a Norton equivalent. All right. And by doing these 4 problems, I will be able to assess whether you know how to do a KCL, how to do KVL. You'll definitely have to use Ohm's law throughout this entire process. So I will be able to assess all of that just by you doing these 4 problems, on top of you knowing how to do the analysis, the different analysis of mesh, node, Thevenin, and Norton. And that's, I know I misspelled equivalent there. Okay. 2, that's half of your midterm exam. The other half of your grade is going to be your lab book. So your lab notebook is due on the day of the exam, and it must be complete up to all the labs except for the maximum power transfer lab, which you guys have. Again, we're going to do that maximum power transfer lab this coming Wednesday, but it's not required to be completed for the exam. Now, some of you ask, can you have a sheet with equations and things like that? And the answer to that is yes. but it will be your lab notebook. Your lab notebook you will be able to look at during your exam, and that is the only thing you will be able to have during the exam on Monday. Your lab notebook, and hopefully it's complete, and your actual exam, and a pencil and a calculator. So really do a good job on that lab notebook before your test. And when you're done with your tests on that day, you will turn in your exam and you will turn in your lab notebook together, and that will be it. So it's going to be open notes basically, but open lab notes. So it's really good that you took very good lab notes. And I think that's about it. Review mesh, review node, review Thevenin and Norton equivalents. Now, I'm not really going to test whether you can do a source transformation. Those are pretty straightforward, but you can use them. So, but use them properly if you're going to, if you need to do a source transformation and it helps you. Okay. And again, the majority of the grading, and I will break it down on the exam. On the front cover, you'll have an exam. It'll tell you the breakdown of the problem. One is your solution. So your solution is going to give you the biggest points, and I normally set that around 60% of your exam percentage of points for each problem. Your final answer, meaning the final numerical answer, if I'm asking for I1 or I2 and I3, those are going to be worth the smallest points, maybe like 5 points apiece if I'm asking for 3 things for you to solve for. Because that final answer isn't what this class is about. The solution in engineering technology is what this class is about. The rest of it is really how well you know your math. And so your math, figuring out that last problem is going to be worth a little less than, it's going to be worth a smaller amount than the actual engineering technology portion of this class. So just realize that your solution is what has to be, it's going to give you the most points. So, and then once you can do the solution, once you can actually do something like with mesh and set up all your equations, you will, the rest of it is just algebra, and you'll be able to just crunch out the numbers. Okay, and that's it. And so I'm going to go ahead and stop the recording.